Great. So now that we've finished reviewing object-oriented concepts in great detail, we can now move on and have a look at some brand new topics. And in this week, we're going to have a look at function pointers and templates. And we've divided those two topics into further subtopics. And within function pointers, we're going to have a look at creating pointers to functions that exist outside of classes, and then pointers to functions that exist within classes, and explore how the syntax differs between the two. Okay, so that's function pointers. And then for templates, we'll have a look at creating templates of functions and then templates of entire classes. So let's start by having a look at creating pointers to functions that exist outside of classes. And so if you remember, we said that the array name itself holds a constant pointer to the first element of the array. So therefore, that array name can be used to access the value of that first element because it holds the memory address of the first element. And that's the same principle when applied to function names as well. The function name itself is a constant pointer that points towards the location that holds the implementation of the function. And we can actually print out this memory address stored at the function name by just printing out the function name without the parentheses, the call operator, the curly brackets, okay, as we see here in the blue box. And of course, to invoke the function, we then add those parentheses, the call operator, so that it dereferences that location, that memory address, to run the code for that function. So as the function names, the array names, the variable names are all pointers that point towards a memory address which stores code or stores a value, we can actually set up pointers to point towards these memory addresses, whether that's for an array, for a function, or for a variable. And in the past, we've had a look at creating pointers for variables as well as pointers for arrays. Now we're going to have a look at creating pointers for functions. And although there is a particular syntax for writing function pointers, which differs a little bit from writing array pointers or variable pointers, the principle is still the same. We can use that pointer as a substitute for accessing the memory address where the code or the values are stored. Let's have a look at the syntax required for creating a function pointer. So when we declare a function pointer, we have to declare it of the matching return type and parameter list to the function that we intend to point to. So if we intend to point to a function that doesn't return a value, then the type of pointer would be void. And if this particular function didn't take a parameter list, then we would have an empty parameter list, an empty pair of parentheses after the pointer name, which by the way goes within a pair of parentheses and has the asterisk there, the pointer symbol, followed by the name. So note there, the full expression is the type, which matches with the function's return type. So if the function doesn't return anything, that's void. And then the pointer name, which is the substitute for the function name. So that's going to be in a pair of parentheses, and then asterisk, pointer name. And then a second pair of parentheses, which corresponds and aligns to the function signature that we want to point to. So if that function is not expecting any parameters, then we don't put anything in the parentheses. But likewise, if it is expecting parameters, such as the example right at the bottom, where it takes two integer values, then we would have to write int, comma, int within the second pair of parentheses there after that pointer name in the first pair of parentheses. And note in this case, this particular function also is going to return an integer. So therefore, we then need to declare the pointer of type integer as well, not void. Okay, so that first type corresponds to return type. Then you have the pointer name, which has the asterisk and enclosed in a pair of parentheses, and that corresponds to the function name. And then the second pair of parentheses is the parameter list, whether that takes any parameters or not. Okay, so that's the syntax that we need to follow for creating a pointer which will point towards a function that exists outside of a class. And then once we've set up that pointer, we can then just assign the function name that we want to point to that pointer. As we see here in the first green box, we would just say pointer name, assignment operator, and then function name without the call operator, because we don't want to call the function, we just want to assign the address that it points to our pointer. So it points towards the same address, basically. And if we look down at the next box, the blue box in the middle of the slide, we see an example here where we've got a function called addNumbers, and we want to assign that address that the function name itself points to our pointer. So we want our pointer to point towards the same address that addNumbers points to. So notice there that we've done that. And then what we can do is we can use that pointer as a substitute for the function name itself. So if you have a look at the final blue box at the bottom of the slide, notice there, rather than calling addNumbers, we can say pointer, PTR, as the function name, and then the call operator after it, passing the parentheses, which in this case are just 5 and 7, presumably adds them together and returns the result, which is then assigned to answer on the left-hand side. Okay, so that pointer, where we assigned it the address of the addNumbers function, what that function name itself points to, we assigned that to PTR, so therefore we can use our pointer as a substitute for the function name. And here we have the full example, so we can put together all the pieces that we've looked at so far. Let's start with the function, which you'll see at the top. It's declared outside of main and not in a class, and it's the add function. So rather than addNumbers, it's just called add, but it takes two parameters, which are two integers. Notice there, int a, int b, and it adds them together and then returns them. So we'll need a return type of int as well there. So just remember that signature there for the function. And now if we come down to main, in the second line is where we create our pointer to this function. So we start with a type of int, which refers to the return type for the add function. So notice there that those correspond. And then we have our function pointer name declared within a pair of curly brackets with the asterisk, and it's called PTR1. And then we open up a second pair of brackets, pair of parentheses, for the two parameters that we want to pass to the function, which are int a and int b. So notice there we've written int, int, close curly bracket, and then semicolon. Okay, so we've declared our function pointer called PTR1 to point towards the add function so that it's set up ready to point towards a matching function signature. And in the next line, the third line below the declaration of the pointer, we are actually assigning the address of add, which is the function itself. Remember, that's called add. And so that function pointer points towards the location where the code for that function is located. And we're going to set our function pointer, PTR1, to point towards the same address that the add function name points to. So that in the line underneath that, rather than writing add there, followed by the parentheses, we can actually replace that with PTR1 so that we dereference that pointer pointing towards the location where that code is stored for the add function, and then we can pass it those two integer values, 6 and 3, pass it to the add function, add them together, and then return them, which is 9, and then store that in an integer variable called answer. And then we just print out the answer. Okay, so I hope that made sense. Hope you managed to follow that through step by step. In the next example, which is actually in the second half of the main function, there's an example where we use typedef. And if you remember, we actually looked at typedef way back in the first week when we were talking about arrays and pointers and references and time. And I don't know if you remember, but at the time, we said that typedef would be useful for defining an alias to a type, saving us having to write it out every time. So it doesn't create a new type, but instead defines an alias for a type. And we can actually apply that here with function pointers. And this will save us having to write out the full expression every single time. So if we're likely to have similar signatures for our functions, then we can actually set up dedicated aliases for functions of that signature. So if you have a look here on this slide, for defining our own custom aliases for function pointers, we can do this by writing the keyword typedef, followed by the return type of the function. So working with the previous example, that would have been the return type of int for the add function. And then we define the alias name, which is a pointer. Okay, so in this case, it's TP. With the asterisk there, and then followed by the parentheses, the actual parameters that are being passed to the function, which again, in the context of the add function, that's 2 integers. So in the blue box there, we've defined that alias TP to be of those types, the return type and then passing the parameters. So therefore, if we want to declare another function pointer to point towards a function of that signature, we can then refer to our alias, in this case TP, rather than having to write it all out again. Okay, so if we go back to our previous slide now, in the second half of the main function, that's where we define our alias for function pointers that point towards functions that have a return type of int and take 2 parameters. And therefore, we can then refer to that type to create the pointer. So notice in the line below, we say TP as the actual alias for functions of that type, and then ptr2. So we create ptr2, the pointer of that type, and therefore we can then assign the address of the add function to ptr2 and did what we did before, where we can actually substitute the add function call for a ptr2 function call, dereferencing that, passing the values, adding them up, returning them, storing them in answer, and then printing out the answer. Okay, so typedef just allows you to create an alias for functions of a particular signature and saves you having to write them out again and again. And of course, this is just for standard primitive types. When we start referring to classes and complex types, of course, those get longer and you may have more parameters. So this is a really convenient and shorthand way to set it up once so that it can be reused later. And so now that we've looked at creating pointers to functions that exist outside of classes, let's now turn our attention to having a look at creating pointers to functions that are declared within a class. And the syntax that we've been using thus far works for pointing towards functions outside of classes, but it won't work for pointing to functions that are declared within a class, even if the function signature corresponds exactly to the type of pointer that we set up with the corresponding return type and parameter list. So the thing that we need to add is the class scope where that function is defined. So if we have a look at the green box here at the bottom of the slide, notice that the pointer to a function declared within the class still has the matching return type and parameter list as before, but the middle section where we declare our pointer with the asterisk within the pair of brackets has to be prefixed with the class name and the scope resolution operator. Because of course, remember, we can have functions of the same signature within different classes. So we have to be specific and refer to which class that we want to point towards. And those functions, whilst of the same signature, are technically stored in unique locations in the memory. So functions of the same signature will have different memory addresses. And say we had an inheritance hierarchy, as we have done in the previous examples, where we have, say, a display function that is declared within the parent and then overridden in the child. Although they have the same signature, they will be unique functions as they have unique implementations. The function in the parent will refer to aspects of the parent, and the function in the child will refer to aspects of the child. So therefore, same signature, but different implementations, and they're stored at different memory addresses. So therefore, that's why we need to be specific and refer to which particular function that we want to point towards. So that's why we write the class name and the scope resolution operator before the pointer to be able to point towards the right function. And furthermore, another aspect that we need to factor in is that member functions of a class are typically called through objects of a class. And unless the member function is explicitly stated to be static, in which it can be called through the class name rather than the object name, for dynamic member functions, or i.e. non-static functions, we would need to call them through an object of a class. So there's actually a different syntax for how we invoke member functions through the pointer. And this actually differs between static objects and pointers to dynamic objects. Okay, so for static objects, we would need to use the object name and then the dot operator, and then the function pointer itself, so the pointer, the function pointer name with the asterisk, and then followed by the arguments. However, for pointers to objects, dynamically assigned memory, we need to dereference via the arrow link. So you'll see in the second green box, within the first pair of parentheses, we would have the object followed by arrow link, and then the pointer name with the asterisk, of course, followed by the arguments. So that's the syntax that we have to abide by, depending on which type of object that we have, whether it's a static object or pointers to objects. And then we also need to explicitly refer to the reference, the memory address of that function we're pointing to. So if you have a look at the green box at the bottom of the slide, in the previous examples where we've referred to functions outside of classes, we could just state the function name there, which refers to the memory address, the location of that implementation, and then assign that straight to the pointer name. But here, we have to explicitly refer to the reference via the ampersand, the reference operator. Okay, so we need to have reference operator and then the class name, scope resolution operator, 2 colons, and then the member function name. Okay, so there's a slightly different syntax there again. So let's put this all together now and have a look at a full example. And here we're sticking with a similar add function example. The only difference is that we've declared it within the context of a class called myClass. All right, so the add function still has the same signature. It takes 2 parameters, 2 integers, adds them together, and then returns them. So 2 integer parameters being passed in, and then has int for return type. So if we come down to the main function now, in the first line, we declare a static object. Notice we're not pointing to anything. Static object of the myClass class. So that's going to inform our use of the dot operator later when we come to call the function through the pointer. But first, let's set up the function pointer. And that's in the second line here, the first emboldened line, where notice we've got a similar format for declaring our function pointer. We start with the return type, which is int, matches the return type of the add function. And then the difference comes in the middle section, where we have to state the class scope. So notice there it's myClass, scope resolution operator, followed by the pointer name, which is asterisk, and then PTR in this case for the pointer name. That's the first pair of parentheses. And then the second pair of parentheses, of course, corresponds to the parameters being passed in to that function, which in this case is 2 integers. So the first and last sections are the same. It's just the middle section where we have to refer to the scope, the class where the function is located. All right, so let's move on now to the next line, which is where we have to refer explicitly to the memory address. And remember before, for functions outside of a class, we can just state the function name. But here, for functions within a class, we have to refer to the reference operator, the ampersand, and then we have the class scope again, so that we're specific. We refer to a particular add function within this particular class, and we want the memory location of that. We want the memory address of that. So that's why we have the reference operator there. And then we can assign that reference to our pointer. So our pointer points towards that memory address. And then in the line underneath that, here is where we refer to the object, the static object that we created. And as it's a static object, we use the dot operator rather than the arrow link. And so here it's obj, name of our object, dot operator, and then asterisk pointer. So that's the substitute of the add function. So rather than saying obj dot add and then the parentheses, it's obj dot asterisk pointer, the pointer name. And then after that, we've got the parentheses with the 2 integers. So that's 3 and 9, add them together, gives us 12. Return 12, and then assign that to our temporary integer variable called answer, and then we just output answer. Okay, so I hope you followed that. It's a similar process to pointing to functions outside of classes. The only difference here is that we have to modify the syntax slightly to be specific to the scope where the function is defined. Okay, here's where we refer to my class and then scope resolution operator. And also we have to abide by the object-oriented principles, where if we're referring to a dynamic member function, then we need to create an object of the class in order to be able to access that dynamic member function. So if it's a static object, it uses the dot operator to then refer to the pointer, which substitutes for the function name. And if it's a dynamic object, we use the arrow link again to then refer to the substitute for the function name, which is our pointer. All right, so just remember this syntax for referring to member functions within a class. Great, so now that we've finished talking about function pointers, let's go on and talk about templates. And we're going to start by talking about templates of functions before we go on to talk about class templates. And so a function template can be a good alternative to overloading functions. If we were to work with the same example that we looked at in the previous slides of an add function, which takes 2 integer parameters, adds them together, and then returns an integer. If we wanted to overload that function, say, to work with floats or doubles or long or short data types, we'd have to declare separate overloads, separate instances of that function, leading to a lot of duplication just to work with specific data types. But function templates, in contrast, allow us to set up the function just once, but we don't have to specify specific types for parameters. Instead, we can set up a generic type so that this can be substituted for the specific type when we call the function. So this would help us to avoid duplicating the functions where we only really change the type of parameters or the return type. That's the only difference between the overloads. The function template allows us to substitute all those instances of specific data types with a generic data type that we can define in the signature of the function. So the syntax that we need for this is the keyword template to go before the declaration of the function. And then we need to follow that with a pair of angled brackets, which if you've used generic classes in Java, that's the same format, where you have to specify the data type or indeed the class within those pair of angled brackets. And then we'd follow that by the function signature. So if we're setting up a given function, we'd have to have the return type, the function name, and then the parameters as usual. Okay, so we've got two options. We can actually, within the syntax of the template declaration, we can either have the keyword class and then give it a alias, a placeholder, if you like, for a specific type, or we can use the keyword type name. And again, follow that with a identifier to substitute for a given specific data type. And that's the syntax required to declare a function template. And then when we come to invoke the function within main, or perhaps within another function somewhere else, we would invoke the function through its name as usual. But then in between the name and the parameters, we have to have a pair of angle brackets to specify the type so that the compiler can actually replace the generic type that was declared within the function template. Every time you call the function, you have to specify what data type you want to work with. Then after the angle brackets, you would specify the parameters as usual. So anything that you're passing to the function, if you set it up to take parameters, then you would have to have those as normal. And let's go on and have a look at an example of this, where here we see that we've got a template function at the top, which isn't actually adding numbers. It's going to compare the two parameters and work out which of the two is the largest and then return that. Okay, so we've set it up at the top with the template keyword, and then we're using the type name keyword within the angle brackets, and then we've specified an identifier T. And then that T is the placeholder for the specific types within the function itself. So you'll notice on the second line that the return type, which would usually be void or int or bool or another primitive type, has been replaced with T for the generic version of the function. And then we've got the function name, and then we've got the parameters, which again have two parameters prefixed with the T generic type. And in this case, we're actually only working with one specific type. So whatever we specify at the point of invoking the function, whatever data type that is, we put within the angle brackets, will become the type that replaces T in all the instances where T is referred to. There's another example later on which we look at where we can specify different aliases, different generic types, so that we can have more than one template generic type. But for now, we're just working with one. So all the instances of T will be replaced by a given type. And you'll notice in the first line of the function here, T result is also of type T, the generic type. And then in the line below, we're using the conditional operator. If you remember the question mark, it goes by lots of different names. Sometimes it's the conditional operator. You may see it as the arithmetic if operator or the ternary operator. And remember, that just returns the left-hand value of the colon if the evaluation is true, or it returns the right-hand value, the right-hand side of the colon if the comparison is false. Okay, so whichever one of the two is greater, it returns that. So if we come down to main now, here's where we invoke the function. So in the first line, get max, notice there within the angle brackets, we specify int. So as we said, all the references to T for this given function call will be replaced with int. So the return type will become int, the first parameter will become int, the second parameter will become int, as will the result temporary variable within the function, so that we can pass integers as we do back down in main. After the specified int data type, we then have the parameters where we pass two integers, 14 and 8, and then the greater of the two is returned and output. And then notice in the line below, the second call to get max, we specify float as the type. So all the references to T will be replaced with floats, so we can pass float parameters. And then in the third call, we specify char. Okay, hopefully you're seeing what's happening. So the template function allows us to declare a generic version of the function with placeholders for a specific type, which can be passed at any given function call. And just before we move on, we've got a note here to say that if the compiler can determine the types of the parameters being passed, then we don't need to explicitly specify it when invoking the template function. So in the first example here, we've got two integers, a and b, that have integer values, so it's clear that they're integers. So therefore, when we pass them to get max, the compiler should hopefully interpret that there's one type being used and these are clearly integers. So it should then replace the placeholders, that generic type that we set up in the function declaration, with the data type int. And this also applies to literal values as well. So if we didn't place integers within variables and we just put them straight into the parameters of the function call, then hopefully again, as they are clearly integers, they're whole numbers, then the compiler would interpret implicitly that the function type is integer. Okay, so this is easy for the compiler to interpret if we're using one clear data type. However, things get a little bit more confusing if we are using a mixture of types and the particular values or the parameters that we're passing could actually fit into multiple data types. Okay, so let's now move on and have a look at an example which uses two generic types. And to make use of more than one generic type, we have to have a separate declaration of another identifier, another placeholder of another generic type. And here in this green box, we've actually used the keyword class, although this does also work with type name as well. The key really is that we have unique identifiers so that the compiler can allocate one name to be substituted for one data type and another name to be substituted for another data type. So if you want to make use of multiple generic types, then first make sure that you set up the function declaration to have those identifiers. And then when you call the function, make sure that you specify the types and explicitly state what each type will be so that it can allocate the given data type to the first generic type and then the second specific data type to the second generic type. And like parameters, they're passed in order. So what you specify for the first type within the function invocation goes to the first generic type, and the second goes to the second. Okay, and let's have a look at an example of this now. Notice we've got the function template declared at the top of the blue box, and we've changed the scenario slightly. It's not get maximum, it's actually get minimum this time. But importantly, notice that before the function name, we've got the declaration of the generic types. And notice now that we've got two. We've got type name T, comma type name U. So we can now handle two unique types, and the placeholder T will be substituted with the first data type specified when we call the function. And then the identifier U, the references to U, will be replaced with the second type defined in the function call. Now, if we have a look at the function signature, which so happens to be on the same line, although it could also be on the line below as we typically see it, but it works both ways. Notice that the first instance of T immediately before the getMin function name is the return type. And then we have the parameters. And the first parameter is of type T. It's identified as A. And then the second parameter is of type U. And it's identified as B. We've also got T result. So that temporary variable within the function will take on the type of the first data type passed to the type name T. And then we perform the, well, it's actually the get minimum this time. It actually returns the minimum of A and B rather than the maximum of A and B. So now if we go down to main, we are declaring two variables within main. We've got int I, which has the value of 10, and then long L, which has the value of 99. So we then pass those values to the getMin function. We invoke it within a cout statement. And importantly, notice there that in the angle brackets, we specify that the first type will be int. So that first type, int, will be substituted for all the references to T. Okay, type name T because it matches with the first generic type declared within the angle brackets of the function. And then the second type, long, will replace all the references to u within the function. Okay, so the compiler will replace those references to t with int and references to u with long, and then perform the function. So it will work out which of the two is the lowest value and then return that. But interestingly, notice that the result variable and indeed the return type of the function is both of type t, which will take on the specific type of integer in this case. So even if the value stored in the long variable, L, passed into the identifier B, even if that long value was the smallest, that may then also be casted to an integer, as that's the type of result, which is also going to be returned of type integer. Okay, so you might just have to watch out for casting there between different types, and that's not a problem at this stage because the value of 99 is an integer, so it would fit nicely into an integer variable and then being returned. But you might just have to watch out for other data types which may not cast as easily or implicitly. You might have to find some explicit way to resolve the conversion from one type to another. Because of course you have to specify a given return type. That can't be decided at runtime. That has to be stated what type that's going to be. So you may just have to cast to that type in order to return a given value. But that's just a small point there to think about. Okay, so we have now had a look at creating template functions. Let's now go on and have a look at creating class templates. And declaring the class to be a template allows all of the data members and the member functions declared within that class to be able to make use of that generic type that's declared within the angle brackets in the template declaration above the class declaration. So we can refer to that generic type, the identifier, in this case t, throughout the entire class. So we could declare data members to be of that type, and we could declare variables and parameters within member functions to be of that type as well. So it's basically allowing class scope rather than function level scope, which we've looked at in the previous slides. And here's an example where we've declared the entire class of vector2d, which is declared at the top of this blue box here, to be a template class. And you'll notice there the template declaration above the class declaration, the class name. And notice there within the angle brackets of the template specifier, we've used the keyword class this time, which is technically more representative of the class rather than type name. But still, we've declared a placeholder, a generic type, with the identifier of t. So within the class vector2d, we can declare a static array, this coordinate array which has two elements to be of type t, and also the constructor in the public interface, vector2d, to have two parameters. It's a non-default constructor in this case because it takes parameters, but those parameters can be of type t. And then when we come down to main and create a object of this class, notice there in the first line of main, we're creating a static object, v, and the class name also has the template angled brackets there, where we specify the data type that we want to then substitute within the class itself, which in this case is int. So that operates on the same principle as the function examples that we've seen so far. We just allow class scope this time. So all of the member functions and indeed data members can make use of this generic type. And technically, there is a difference between the syntax of member functions which are declared to be inline, and this is the particular method I've been demonstrating within some of the previous practicals where I've declared the implementation for the function at the same place as declaring the prototype for the function. So that's what we call inline, as opposed to declaring the implementation for the function separate to the interface, meaning that the prototype is declared within the header and the implementation could be declared within the header as well, but it would have to sit outside the declaration of the class, typically below it. Okay, and also in previous examples as well, we've put that in a different file. We've put it in the CPP file as well, so it's still external to the inline implementations that I've demonstrated recently. But if we're not going to implement our functions inline, we would actually have to use a different syntax where we have to precede the implementation of the function, where we have the scope, the return type, the function name, and the parameters with the template specifier as well. So here in the green box, you'll notice that all of the function implementations outside of the prototypes will also have to be prefixed with the template specifier. So it's the same format where we'd write the keyword template and then angle brackets and then keyword class followed by an identifier. And then that identifier could be used in the return type of the function, which it is in this case. And we also then have the class scope as well. So we have the class scope followed by the angle brackets, again, the generic type. And then we have the scope resolution operator, the 2 colons, and then the function name. So the only thing that's new here is the generic type that sits in between the class name and the scope resolution operator. And that mirrors the previous example where we declared the entire class to be of generic type. So that's why we have to have the angle brackets following the class name. And if we have a look at this example here, notice that we've moved the constructor definition outside of the class declaration. And of course, remember that the constructor doesn't have a return type. So if you notice below the class declaration here, we've got the template specifier and then the angle brackets with class, keyword class, and T, the identifier, which is exactly the same as the line that sits above the class declaration itself. As you see, the very first line at the top of this blue box here, above the declaration of the vector2D class. And so if we go back down to the bottom of the blue box here, the constructor definition, which is external to the class declaration, notice here that the line after the template specifier is the class name. We've omitted the return type, of course, because the constructor doesn't have a return type. So it's just the class name followed by angle brackets T, the generic type, scope resolution operator, 2 colons, and then the function name, which is the constructor, again, same name as the class, and then the parameters. Okay, so that's just a slightly different format if we are not going to be declaring the implementation for functions in line with the class declaration. And finally, here we've got an important warning that tells us that we can't actually use the template keyword within the CPP files. So building upon what we just looked at, we can declare our template functions within a class in line within the header file. So what I've been doing recently, we've put in the implementation within the same place as the prototype for the function within the class declaration. Or you can use the alternative format in the previous slide where you declare the prototype for the function in the class declaration and then implement it outside of that class declaration, but still within the header file, not within the CPP. I think the current version of Visual Studio will still generate a linker error if we try and have our function definitions within the CPP. Okay, so just remember, if you're creating template classes, to put them within the header file only. Okay, and that brings us to the end of the presentation. So let's now transition and have a look at some of the exercises for this week. Great, so let's dive into the first exercise for this week, which is regarding function pointers. So if we have a look here, our first exercise is to set up 2 functions one named hello message, which just prints hello, and another which is goodbye, and that prints goodbye to the screen. Okay, so fairly simple functions to start with. Don't take any parameters, and the return type is void. And then within our main, we just want to create a function pointer, and we first of all set it to point towards the hello message function so that we can invoke that, and then we reuse that pointer to point towards the goodbye function, and then invoke that through the same pointer. Okay, so let's set up the hello message. This is just a function outside the context of a class. The later exercises look at using classes. Let's just say hello message. Here, and within that, we just want to print out hello. Okay, so fairly simple. Hopefully it won't be a challenge for you. And then we also want to set up another one for goodbye. So let's do something similar. Goodbye message or goodbye, one of the two, like that. And again, just print out goodbye. All right. And again, no parameters either, and the return type's void. Okay, so that should be all we need to get started. And then within our main comes the function pointer creation. So remember, we have to match the return type when creating the pointer. So that's void for both functions, okay, and particularly in this case. And then we create our pointer within a pair of parentheses. I just call my pointer for now. It's generic name as we're going to reuse it. And then we have the parameters. And in this case, because we are not passing any parameters, we can leave that empty. All right. And then just have a semicolon there. Great. So that's our single pointer. And first of all, let's assign it the address of the hello message function. And remember that the function name holds the constant pointer to the implementation of the function. So we just have to say pointer assigned the function name. And remember, don't have the parentheses there because otherwise you'll invoke the function. You just want to pass the actual reference, the memory address of this function and assign it to your pointer. So that in the next line, you can then invoke it using the call operator, the parentheses, through the pointer name rather than the function name. All right. And then what we'll do after that is we just retarget the pointer to point towards goodbye. Again, just the function name. And then we can call that again through here. Okay, so let's see whether this runs correctly. Yeah, and there we go. Notice there that we have printed out hello and goodbye. So that shows that we are correctly invoking the functions. Good. All right. Okay, so let's take this a little bit further then. In the second exercise, we are going to merge these specific outputs into one generic function that can be reused, and we can customize it. And we're going to set up a parameter, a constant string parameter, which is then displayed on the screen. So we can get rid of one of these. And if I just modify hello message and make it message, and then set up a string parameter. In this case, we're asked to make a constant string parameter, just in case, we don't want to change it. And let's just say message there. Okay, and then rather than printing out the literal string value of hello, let's print out our parameter, message, so that what we now have to do when we come down to our pointer declaration, we want to now specify that we have one parameter and it's of type string. Okay, so we can now retarget the pointer to message, the generic function, and then of course we have to pass it a literal value to print out. So in this case it was hello first time, and then the same again. Yeah, so that would just be passed into the constant string message and then printed to the screen. And then we're going to have to still point towards message there, but we just want to pass goodbye now. So let's do that here. Okay, great. And let's run this again. And we should see the same output, just with a generic function this time where we customize the parameter as we do there. Okay, so maybe this is a bit more efficient way to do it, and also helps us to reformat our pointer to get used to parameters. Okay, so hopefully that gets you started there. Have a go at the other exercises where I think you'll go on to create member functions within classes, and remember that the syntax for creating pointers to member functions is slightly different. So remember that, go back to the slides if need be. So work through those exercises there. And just before we finish it, I just want to get you started with function templates, because that's the other main concept that we had a look at this week. So let's just have a go at exercise 8. So let's just say here, exercise 8. And better put a new line there as well. There we go. All right, just a bit of formatting. And what do we want to do? We want to create a template function named display array that returns void and has two parameters, one being a pointer to an array and the second being the size of the array. Okay, let's pause there, because that's going to involve two generic types, isn't it? We want one type for the pointer to an array, and then another type for the size of the array. So that's probably just an integer. And then let's have a look here. I think we're going to create two separate arrays later, which are of integer type and then a float. So we'll probably want to create that second. We want to change the first one. Sorry, it's the first one we want to change, and it's the second one which stays the same. So best to have two different generic types there. Okay, so let's start off by creating this display array function. And let's put that here. So remember, it's the template keyword. And then here's where we want to open the angle brackets. And we want to, in this case, create two generic types. So you can use type name or class. I'm going to use class for now. And the identifier is up to you. I'm going to stick with what we've looked at so far in terms of one named T and one named U. Okay, so representing two generic parameters there. That two generic types which can be used within the function we're about to create. So it's a void return type, and the name is display array, and it's going to take the pointer to the array. So that's going to be the first parameter. And let's just say that's going to be a pointer there to our array. And just to avoid the keyword array, I'm going to make it a pointer because it would be to that. Yeah, and then here is going to be the second parameter, which is size. So let's just give that the name of size. Right, so within here, I just want to output the array. Yeah, so it's set up for any array. So let's create a loop. Whilst I guess the type U is probably going to be int most of the time. I'm just going to explicitly state this as type int, as that's not going to change. We're always going to increment in whole numbers, so that's probably best left as an int. Okay, and then for the array, every element, let's just print it out. So let's just say C out there. And also that's in the line, so it's on the next line. Okay, so that should be our template function created. Now we have to go about invoking it, and we also need to set up this array to pass to it as well. So let's create the first array. Let's say int array. It's of 9 elements, and just to be nice and quick, I'm going to use the braces here to specify 9 values. Let's go up to 8. Okay, and then let's also do the same for float as well. We're going to do that later. Let's call that float array. Same again, 9 elements. And we could make these decimals, I suppose. We can add some decimal places onto them. Let's just make them up as we go. Oops. 1.5, 1.8, 1.9. 0.4, 0.2, 5, and 2. Just make them up. 9. There we go. Hopefully that's good enough for now. And now, oh, did I put the semicolon? Let's just check. No, I didn't. So semicolon there. There we go. Sorry, struggling to see here. And now we just want to we want to invoke the display array function. There we go. And remember, in between the function name and the parameters, parentheses, we want to write the types that will be substituted in the template function. So the first one is going to be int in this case, and then it's int again for our int array. So we can pass in the reference of int array to our pointer, and we also want to specify the size as 9 elements, and then let's have a new line and then call it again, this time specifying that the first type is going to be float, and we want to pass float array. So let's give it a run and see what happens. Hopefully we will see 2 lists. There we go. We've got our integers there and then our floats there. So we've successfully created the template function to work for both int and float values. There we go. Okay, so hopefully that gives you something to start with there for function pointers and also templates. Have a go at the remaining exercises and see how you get on.